Chapter 3, Types and Classes. In this chapter, we introduce types and classes, two of the most fundamental concepts in Haskell. We start by explaining what types are and how they are used in Haskell, then present a number of basic types and ways to build larger types by combining smaller types, discuss function types in more detail, and conclude with the concepts of polymorphic types and type classes. 3.1 Basic Concepts. A type is a collection of related values. For example, the type bool contains the two logical values false and true, while the type bool to bool contains all functions that map arguments from bool to results from bool, such as the logical negation function not. We use the notation v::T to mean that v is a value of the type t, and say that v has type t. For example, false has that type bool, true has type bool, not has type bool to bool. More generally, the symbol : can be used with expressions that have not yet been evaluated, in which case the notation e is of type t means that evaluation of the expression e will produce a value of type t. For example, not false is of type bool, not true is of type bool, not false is of type bool. In Haskell, every expression must have a type, which is calculated prior to evaluating the expression by a process called type inference. The key to this process is the following simple typing rule for function application, which states that if f is a function that maps arguments of type A to results of type B and E is an expression of type A, then the application f of E has type B. For example, the typing not false is of type bool can be inferred from this rule using the fact that not is of type bool to bool and false is of type bool. On the other hand, the expression not 3 does not have a type under the above rule, because this would require that 3 is of type bool, which is not valid, because 3 is not a logical value. Expressions such as not 3 that do not have a type are said to contain a type error and are deemed to be invalid expressions. Because type inference precedes evaluation, Haskell programs are type safe, in the sense that type errors can never occur during evaluation. In practice, type inference detects a very large class of program errors and is one of the most useful features of Haskell. Note, however, that the use of type inference does not eliminate the possibility that other kinds of error may occur during evaluation. For example, the expression 1 divided by 0 is well typed, but produces an error which, when evaluated, because the result of division by 0 is undefined. The downside of type safety is that some expressions that evaluate successfully will be rejected on type grounds. For example, the conditional expression if true then 1 else false evaluates to the number 1 but contains a type error and is hence deemed invalid. In particular, the typing rule for a conditional expression requires that both possible results have the same type, whereas in this case, the first result, 1, is a number and the second, false, is a logical value. In practice, however, programmers quickly learn how to work within the limits of the type system and avoid such problems. In GHCI, the type of any expression can be displayed by preceding the expression by the command type. For example, :type not is of type bool to bool. Basic types. Haskell provides a number of basic types that are built into the language, of which the most commonly used are described below. Bool, logical values. This type contains two logical values, false and true. Char, single characters, or char maybe. This type contains all single characters in the Unicode system the international standards for representing text-based information. For example, it contains all characters on a normal English keyboard, such as A, and 3, and underscore, as well as a number of control characters that have a special effect, such as newline and tab. As in most programming languages, single characters must be enclosed in single forward quotes. String, strings of characters. This type contains all sequences of characters such as ABC, and 1 plus 2 is 3, and the empty string. Again, as is standard in most programming languages, strings of characters must be enclosed in double quotes. Int, fixed precision integers. This type contains integers such as -100, 0, and 999, with a fixed amount of memory being used for their storage. For example, the GHC system has values of type int in the range -2 to the 64 to 2 to the 63 minus 1. Going outside this range can give unexpected results. For example, evaluating 2 to the 63 type of int gives a negative number as the result, which is incorrect. The use of type of in this example forces the result to be an int rather than some other numeric type. Integer, arbitrary precision integers. This type contains all integers, with as much memory as necessary being used for their storage, thus avoiding the imposition of lower and upper limits on the range of numbers. For example, evaluating 2 to the 63 of type integer using any Haskell system will produce the correct result. Apart from the different memory requirements and precision for numbers of type int and integer, the choice between these two types is also one of importance. In particular, most computers have built-in hardware for fixed precision integers, whereas arbitrary precision integers are usually processed using the slower medium of software as sequences of digits. Float, single precision floating numbers. This type contains numbers with a decimal point, such as -12.34, 1.0, and pi, with a fixed amount of memory being used for their storage. The term floating point comes from the fact that the number of digits permitted after the decimal point depends upon the size of the number. For example, evaluating square root of 2 float using JCI gives the result 1.4142135. The library function square root calculates the square root of a floating point number, which has 7 digits after the decimal point, whereas square root of 999 float gives 3162262, which only has 4 digits after the point. Double precision floating point numbers. This type is similar to float, except that twice as much memory is used for storage of these numbers to increase their precision. For example, evaluating square root of 2 double gives more things behind the comma, or the decimal point. Using floating point numbers is a specialist topic that requires a careful treatment of rounding errors, and we don't often use such numbers in this book. We conclude this section by noting that a single number may have more than one numeric type. For example, the number 3 could have type int, integer, float, or double. This raises the interesting question of what type such numbers should be assigned during the process of type inference, which will be answered later in this chapter when we consider type classes. List types. A list is a sequence of elements of the same type, with the elements being enclosed in square parentheses and separated by commas. We write square brackets with a t inside for the type of all lists whose elements have type t. For example, the list containing false, true, false is of type list of bool, and so on. The numbers of elements in a list is called its length. The empty list of length 0 is called the empty list, while lists of length 1, such as the list containing false, list containing the character A, and the list containing the empty list are called singleton lists. Note that the list containing the empty list and the empty list are different lists, the former being a singleton list comprising the empty list as its only element, and the latter being simply the empty list that has no elements. Now I want to try something. Does the empty list, how do you do equals in Haskell? Is it double equals? See, I find that is, why did they design it that way? So strings are really just lists of characters, I think. Like, what? Why do they do it that? If they're so into types, why are strings just lists? Strange. There are 3 further points to note about list types. First of all, the type of a list conveys no information about its length. For example, the list true-false and false-true-false both have type bool, even though they have different lengths. Secondly, there are no restrictions on the type of the elements of a list. At present, we are limited in the range of examples that we can give because the only non-basic type that we have introduced at this point is list types. But we can have lists of lists, such as... Oh, wait, what? So there is a difference. How do you do this? Oh. So why does the equals function say that a list of characters is the same as a string? That's strange. Finally, there is no restriction that a list must have a finite length, in particular due to the use of lazy evaluation in Haskell. Sorry for hitting the microphone. Lists with an infinite length are both natural and practical, as we shall see in chapter 15. Tuple types. A tuple is a finite sequence of components of possibly different types, with the components being enclosed in round parentheses and separated by commas. We write T1, T2, up to Tn for the type of all tuples whose ith components. All right, I got interrupted for a bit. We write T1, T2, Tn between round brackets for the type of all tuples whose ith component have type Ti for any I in the range 1 to n. For example, false true is of type tuple bool bool, and so forth. The number of components in a tuple is called its arity. The tuple, empty tuple, of arity 0 is called the empty tuple. Tuples of arity 2 are called pairs, tuple of arity 3 are called triples, and so on. Tuples of arity 1, such as the tuple containing false, are not permitted because they would conflict with the use of parentheses to make the evaluation order explicit, such as 1 plus 2 times 3. In a similar manner to list types, there are 3 further points to note about tuple types. First of all, the type of a tuple conveys its arity. For example, the type bool char contains all pairs comprising a first component of type bool and a second component of type char. Secondly, there are no restrictions on the types of the components of a tuple. For example, we can now have tuples of tuples, tuples of lists, and lists of tuples. The tuple containing A and the tuple false B is of type tuple char to tuple bool char, and so forth. Finally, note that tuples must have a finite arity in order to ensure that tuple types can always be inferred prior to evaluation. 3.5 Function types. A function is a mapping from arguments of one type to results of another type. We write T1 goes to T2 for the type of all functions that map arguments of type T1 to result of type T2. For example, we have not is of type bool to bool, even is of type int to bool. The library function even decides if an integer is even. Because there are no restrictions on the types of the arguments and results of a function. The simple notion of a function with a single argument and a single result is already sufficient to handle the case of multiple arguments and results by packaging multiple values using lists or tuples. For example, we can define a function add that calculates the sum of a pair of integers and a function 0, 2 that returns a list of integers from 0 to a given limit, as follows. In these examples, we have followed the Haskell convention of preceding functions function definitions by their types, which serves as useful documentation. Any such types provided manually by the user are checked for consistency with the types calculated automatically using type inference. Note that there is no restriction that functions must be total on their argument types, in the sense that there may be some arguments for which the result is not defined. For example, the result of the library function head that selects the first element of a list is undefined if the list is empty. I wonder, oh yeah, exception. Oh, he was going to do that. Exception. Curried functions. Functions with multiple arguments can also be handled in another, perhaps less obvious way, by exploring the fact that functions are free to return functions as results. For example, consider the following definition. Add from int to a function from int to int. Add xy is x plus y. Okay. It's just like a normal curried functions, but these brackets, parentheses, are optional, I think, because creating is, function types are right associative. More precisely, add takes an integer x and returns a function in which turn takes an integer y and returns the result x plus y. Note that the function add produces the same final result as a function add from the previous section, but whereas add takes its two arguments at the same time, packaged as a pair, add prime takes its two arguments one at a time as reflected in the different types of the two functions. Add goes from a pair of ints to int, and add prime goes from int to int to int. Functions with more than two arguments can also be handled using the same technique by returning functions that return functions and so on. For example, a function mult that takes three integers x, y, and z one at a time and returns their product can be defined as follows. This function states that mult takes an integer x and returns a function, which in turn takes an integer y and returns another function, which finally takes an integer z and returns the result xyz. Functions such as add prime and mult take their arguments one at a time. Are called curried functions. As well as being interesting in their own right, curried functions are also more flexible than functions on tuples because useful functions can often be made by partially applying a curried function with less than its full complement of arguments. For example, a function that increments an integer can be given by the partial application add prime of 1 of the curried function add prime with only one of its arguments. To avoid excess parentheses when working with curried functions, two simple conventions are adopted. First of all, the function arrow in types is assumed to associate to the right. For example, the type int means int, the same with parentheses. Consequently, function application, which is denoted silently using spacing, is assumed to associate to the left. For example, the multiplication mult of xyz means this. Unless tupling is explicitly required, all functions in Haskell with multiple arguments are normally defined as curried functions, and the two conventions above are used to reduce the number of parentheses that are required. In Chapter 4, we will see how the meaning of curried function definitions can be formalized in a simple manner using the notion of lambda expressions. So I wonder, I think some does Haskell have how do you say that? Does Haskell have variable argument functions, like a function that works on a list of numbers, but you don't have to put them in a list first, you can just pass it as arguments? I don't know. 3.7 polymorphic types. The library function length calculates the length of any list, irrespective of the type of the elements of the list. For example, it can be used to calculate the length of a list of integers, a list of strings, or even a list of functions. Length of the list 1, 3, 5, 7 is 4. Length, yes, no is 2. Length, sinus, cosine, tangent is 3. The idea that length can be applied to lists whose elements have any type is made precise in its type by the inclusion of a type variable. Type variables must begin with a lowercase letter and are usually simply named ABC and so on. For example, the type of length is as follows. Length of the list of A's. Length is a function from lists of A's to int. That is, for any type A, the function length has a type A to int. So you don't have to specify that of which type class A is. Foldable. Okay, so T is like a list-like thing, I think. Foldable means that you can run fold on it, I think. And then A is not specified here, so it's any type. So you don't have to specify the type class. For example, first goes from a tuple of type A and B to A. And these other ones are also like that. The type of a polymorphic function often gives a strong indication about the function's behavior. For example, the type A, list of A's to list of B's to a list of AB's. We can conclude that zip pairs up elements from two lists, although the type on its own doesn't capture the precise manner in which this is done. Overloaded types. The arithmetic operator plus calculates the sum of any two numbers of the same numeric type. For example, it can be used to calculate the sum of two integers, or the sum of two floating point numbers. 1 plus 2 is 3, 1 plus 0 plus 2.0 is 3.0. The idea that plus can be applied to numbers of any numeric type is made precise in its definition by the inclusion of a class constraint. Class constraints are written in the form of CA, where C is the name of a class, and A is the type of a variable. For example, the type of the addition operator plus is as follows. Plus is of type A to A to A, where A is of the class num. That is, for any type A that is an instance of the class num of numeric types, the function plus has type A to A to A to A, A to A to A. Parenthesizing an operator converts it into a curried function, as we shall see in chapter 4. A type that contains one or more constraints is called overloaded, as is an expression with such a type. Hence, num A to A to A to A, is an overloaded type, and plus is an overloaded function. More generally, most of the numeric functions provided in the prelude are overloaded. For example, multiplication, negate, and apps. Numbers themselves are also overloaded. For example, 3 is of type num AA. Interesting. Means that for any numeric type A, the value 3 has type A. That for any numeric type A, the value 3 has type A. In this manner, the value 3 could be an integer, a floating point number, or more generally, a value of any numeric type, depending on the context in which it is used. Basic classes. Recall that a type is a collection of related values. Building upon this notion, a class is a collection of types that support certain overloaded operations called methods. Haskell provides a number of basic classes that are built into the language, of which the most commonly used are described below. More advanced built-in classes are considered in part 2 of the book. Equality types. This class contains types whose values can be compared for equality and inequality using the following two methods. All right, I got interrupted again. I don't know where I was, but This class contains types whose values can be compared for equality and inequality using the following two methods, equals and not equals. All the basic types bool, char, string, int, integer, float, and double are instances of the EQ class, as are list and tuple types, provided that their elements and component types are instances. For example, false equals false is true, AB false, ABC true. Note that, they don't show off the fact that strings are equal to lists here. Note that function types are not in general instances of the EQ, equality class, because it is not feasible in general to compare two functions for equality. Order types. This class contains types that are instances of the equality class EQ, but in addition, whose values are totally linearly ordered, and as such can be compared and processed using the following 6 methods. Less than or equal, greater than or equal, min and max. All the basic types bool, char, string, int, integer, float, and double are instances of the ord class, as are list types and tuple types, provided that their element and component types are instances. For example, false is less than true is true. What? That's weird. Min A, B, A, elegant, elephant, true, false, true. Note that strings, lists, and tuples are ordered lexicographically, that is, in the same way as words in a dictionary. For example, two pairs of the same type are in order if their first components are in order, in which case their second components are not considered, or if their first components are equal, in which their second components must be in order. Showable types. This class contains types whose values can be converted into strings of characters using the following method, show a to string. All the basic types bool, char, string, int, integer, float, and double are instances of the show class, as are list types and tuple types, provided that their element and component types are instances. For example, show false, show a, show 1, 2, 3, show list 1, 2, 3, show a false. Readable types. This class is dual to show and contains types whose values can be converted from strings to characters using the following method. Read is a method from strings to a. All the basic types bool, char, string, int, integer, float, and double are instances of the read class, as are list types and tuple types, provided that their element and component types are instances. For example, read of false type bool is false. The use of type of in these examples resolves the type of the result, which would otherwise not be able to be inferred by GHCI. In practice, however, the necessary type information can usually be inferred automatically from the context. For example, the expression not read false requires no explicit type information because the application of the logical negation function not implies that false must have type bool. Note that the result of read is undefined if its argument is not syntactically valid. For example, the expression not read ABC produces an error when evaluated because ABC cannot be read as a logical value. Not read ABC, exception, prelude, no parse. Numeric types. This class contains types whose values are numeric, and as such, can be processed using the following 6 methods: plus, minus, times, negate, and abs. What is that? Signum? The method negate returns the negation of a number, abs returns the absolute value, while signum returns the sign. Oh, there should have been an enter here. Okay. The basic types int, integer, float, and double are instances of the num class. For example, 1 plus 2 is 3, blah blah blah. As illustrated above, negative numbers must be parenthesized when used as arguments to functions to ensure the correct interpretation of the minus sign. For example, abs minus 3 without parentheses means abs minus 3. Huh? Oh, okay, there. Okay, which is both the incorrect meaning here and an ill-typed expression. Note that the num class does not provide a division method, but as we shall now see, division is handled separately using two special classes, one for integral numbers and one for fractional numbers. Integral types. This class contains types that are instances of the numeric class num, but in addition whose values are integers, and as such support the methods of integer division and integer remainder. Divs from A to A to A, mod from A to A to A. In practice, these methods are often written between their two arguments by enclosing their names in single back quotes. The basic types int and integer are instances of the integral class. For example, 7 div 2 is 3, 7 mod 2 is 1. For efficiency reasons, a number of prelude functions that involve both lists and integers, such as take and drop, are restricted to the type int of finite precision integers, rather than being applicable to any instance of the integral class. If required, however, such generic versions of these functions are provided as part of an additional library called data list. Fractional types. This class contains types that are instances of the numeric class num, but in addition whose values are non-integral, and as such support the methods of fractional division and fractional reciprocation. Divide and recip. The basic types float and double are instances. For example, 7.0 divided by 2.0 is 3.5. Chapter remarks. I wonder if we do 0. How do you do this again? 0.3 divided by 0.2. Yeah, okay. Chapter remarks. The term bool for the type of logical values celebrates the pioneering work of George Boole on symbolic logic, while the term curried for functions that take their arguments one at a time celebrates the work of Haskell Curry, after whom the language Haskell itself is named. On such functions, the relationship between the type of a polymorphic function and its behavior is formalized in an appendix, I suppose. A more detailed account of the type system is given in the Haskell report, and a formal description of the type system can be found in 5. 3.11 Exercises. What are the types of the following values? Notes. Oh. What is this? Okay. This is a list of characters. Haskell. This is a tuple of care. This is a list of bool and care. This is a tuple of a list of bools and a list of cares. This is a list of functions from from tail. How does tail work? From A to A. Like this, I hope. Let's check. Yes. Oh, what is it doing now? Lexical error. Excuse me. Huh? Oh, these are those weird quotes from the ebook. Okay. That's annoying. Yes, we got that right. I mean, I think we have the exercise correct. I'm not going to check everything. The last one is kind of hard though, so maybe, I mean hard. Yes, we got it right. Write down definitions that have the following types. It does not matter what the definitions actually do as long as the type is correct. Bools. Okay, let's see. Bools is true. Yeah. Nums. A list of lists of numbers. Wait. Add of A, B, C is A plus B plus C. Oh. Okay. I think maybe I need to explicitly say that it's from int, but I can only do that in a file, I think. What was I writing before? Hello? Oh yeah, okay. Add of A, B, C is A plus B plus C. Add is of type int. Okay, I don't know if that counts. Copy goes from A to a pair of A's. Okay, so copy A is equal to A. Yeah, it automatically gave it a B though instead of A, but I think it's fine. Apply function from A to B to A gives B. Okay. Apply f A equals f of A. Apply type of apply. Yeah. It's weird how it chooses those type variables though. Like, why is it calling it T1 instead of A and B? What are the types of the following functions? Okay, second. Wait, let's write this in the notes. Second is from a list to A. Swap is from A to B, AB to BA. Pair is from AB to AB. Oh wait. Like that. Double. How do you write that? Is num A from A to A. Palindrome is from strings. Oh no, is from lists of A's to bool. And twice is from a function of A to B. Oh no, from A to A, I think. To, oh yeah, then it takes another A, then it returns an A. Alright, exercise 5. Why is it not feasible in general for function types to be instances of the egg class? When is it feasible? Hint. Two functions of the same type are equal if they always return equal results for equal arguments. I think the reason is that types might be infinite. Like there's an infinite amount of lists. And even if they're not infinite, like checking all ints for two functions is really hard. You could like maybe prove that they're the same, but I don't think such a mechanism exists in Haskell. So that's my answer for exercise 5. And therefore we've finished chapter 3. Chapter 4, defining functions. See you next time.